Thanks. All right, thank you. And I sound pretty loud, aren't I? Okay, thank you, and welcome to this tutorial. I'm Bob Morris from NASA Ames Research Center, and my colleagues are Roman Barták from the Charles University in Prague, and Kristen Brent Venable from Tulane University and the Institute for Human and Machine Cognition. And here's an outline. Well, here's the scope of our tutorial. We're not going to explain the mysteries of time in the universe. We're going to really get more concrete and talk about machine representations of time, but not even all machine representations of time, only those based on graphical representations of time. So the idea being, in a graphical representation of time, the node elements have variables that take on time values, and the edges represent temporal orderings or duration constraints. And we're going to look at a series of algorithms and techniques for processing temporal data using constraint reasoning methods. And there are two broad types of reasoning methods that we're going to look at, those based on inference and those based on search. So we'll break it down. I will talk about 20 minutes, give you some introductory remarks, then we'll turn it over to Roman, who will talk about sort of the core approaches to temporal reasoning and based on constraints. Then after the break, Brent will take over and talk about more recent extensions to temporal reasoning systems. And then I'll close with a discussion of some of the applications in planning and plan execution systems, and also some applications in information processing of the techniques that we're going to be talking about in this paper. So I'm going to kind of give an unscientific overview of representations of time, and the idea that the techniques that we're going to talk about in this tutorial are a synthesis of many different kinds of approaches that have come before this approach was invented. I wanted to just introduce you to some history of visualizations of time that'll kind of recur. We'll kind of reference modern versions or modern refinements of these notions. This is the Chronicle of Eusebius from the 4th century. The chronicles go back to ancient times, where you basically have each row represents a time duration, and there's an entry for some historical event. So this is sort of a precursor to a temporal database kind of representation, where you have time-stamped information, and that goes back to ancient times. There's timelines. We'll see examples of timelines in machine representations of temporal reasoning too. In the 18th century, Joseph Priestley from England invented, I guess, although it's not clear when timelines were invented, but timelines are a nice way of distilling temporal information from other kinds of information, because you have time represented on the x-axis, and you have certain events or things that have happened represented as durations on this timeline. I just wanted to point out, I was reading about this in an interesting book on history of timetables, and Lawrence Sterne, who's the author of Tristan Shandy, a satirical novel of the 18th century, about the same time that these timelines came out, satirized the notion of that time is linear. He was referring to the perception of time, which is distinctly nonlinear. We go back and forth from past to future, and he said, and Sterne was saying, instead of a line, we should be using squiggles to represent the flow of time, because that was how time is perceived. So we're going to focus more on graphical representations. Here are two graphical representations, early graphical representations of time. It's a critical path method schedule from the 1950s. This was the first kind of early graphical representation where you represent events with dependencies included. I'll get back to that in a minute. And then we'll go in the more modern era. Here's a constraint plan graph, and I'll talk about that in the application section. This is another kind of an example of a graphical representation of time, where these are events or actions, and the temporal relations are represented by these edges between the endpoints of these durations. And we'll see a lot of that in this tutorial. just as a final kind of outrageous look at visualization of time, this is the temple of time from the 19th century. Someone had an idea of kind of combining chronicles with timelines. So this is a temple, meant to be a temple, and the floor is a timeline, and the columns represent sort of important information. So this was made in the 19th century, so you can see the 19th century column is only half finished. And each of these columns has important either people or events happening. So it's sort of an interesting. And then you have the beginning of time, or the creation, back at the other end of the temple. So these are sort of more audacious representations, visualizations of time that have been proposed. Obviously, this doesn't have a lot of practical use. So really, I think this one of the starting points for talking about machine representations of time is the early 1910s, where the Industrial Revolution sort of induced the realization that planning and scheduling is a very hard problem for large applications. So around the 1910s, you had separation. You had committees or groups in large organizations. One side doing planning or sequencing, and the other side doing scheduling. And both of those were really hard tasks. And so you had refinements to these basic notions of timelines and chronicles. Henry Gantt invented his famous Gantt chart, which allowed representation of temporal information. And then, of course, with transportation, the growth of transportation, you had timetables as sort of a refinement of the chronicle notion. And then in the 1950s, you had early mathematical formulations of scheduling problems using linear programming, critical path method, PERT, all these sorts of methods for scheduling emerged. It is alleged, I read somewhere, that the onset of sort of a graphical representation of temporal information arose in order to explain to managers what all these linear programming constraints meant. They were represented as equations, but managers didn't know exactly what these constraints meant. So some of the schedulers had to draw on the blackboard what these constraints meant, and they were represented graphically. So that was kind of an interesting piece of folklore. And DuPont, the DuPont company had one of the earliest examples of one of the earliest computers, and they were trying to find something to do with it. It sort of sat around being unused. And the CEO of DuPont said, find something to do with this UNIVAC that we have that's not doing anything. And someone proposed that, well, scheduling might be something we could do on it. And so early use of computers to do scheduling actually was just in order to find something to do with a machine that was like lying around in the DuPont company. So then also in the 50s and 60s, we had the emergence of mixed initiative linear programming and dynamic programming methods for scheduling. With the advent of complexity theory in the 1960s and 70s, you had a development of the hierarchy of scheduling problems based on their complexity. And also in the 60s, you had numerical methods for trajectory optimization, which trajectory optimization often optimized in terms of time as its optimizer. In the 1950s, Arthur Pryor published a book called The Logic of Time, which proposed the use of logic in order to represent the temporal reasoning, realizing that time was used to represent change in the truth of a proposition. And then that was the development of formalizations of time based on linear relationships, based on a timeline, and the formulation of modal logics of time, where you represent time syntactically as an operator on propositions. And then more interest to AI people is the first order representations of time that were developed in the 1960s by philosophers like Donald Davidson, who proposed what's called the method of temporal arguments, which is simply the idea time can be represented as an argument in a predicate, like when you say an event happened at a time. At is a relationship between an event and some point in time. So the method of temporal arguments, that's called the method of temporal arguments, it was very influential in the development of machine representations of time in the 1980s by people like James Allen, who used the same kind of first order representation of time in his work on temporal reasoning. And then we have another representation, a graphical representation of time involved network flows over time, which are called dynamic flows. So if you want to apply a network flow representation to solving problems like how many cars can streets of a town serve, if you use the standard network flow, the only thing you can really extract from a flow problem is sort of the maximum capacity of the town streets. Whereas if you employ dynamic flows, you're representing the evolution of a network flow over time, and so you have an explicit representation of time in your network. And that was another influential kind of component to the graphical approach that we're going to be talking about. And then of course with dynamic flows and network flows in general, you have the application of shortest path algorithms in order to solve some of these flow problems. And we'll see shortest path algorithms later in this tutorial applied to temporal reasoning problems. And then you have temporal databases that were merged in the 70s and 80s, extensions to relational database theory. As I mentioned, there's sort of a modern version of the chronicle that I showed you earlier. And then finally, the application of temporal logics to verification and validation of programs or hardware using temporal logics. But we're not going to talk about temporal logics in this tutorial, but that's another kind of rich tradition of use of time in computation. So then when we get to AI and AI representations of time, that kind of emerged over the process of reasoning about change. In the situation calculus and other early representations, the representation of change and action, and the effects of action. So here is an example. After the stock goes above a certain amount, X dollars sell. That's an example of where a state of the world changes to state of the world trigger certain actions. So the planning formulations, early planning formulations, involved representing change in terms of state, in terms of actions, the effects of actions. But then it became realized that sometimes time itself is a trigger of change. So to make mortgage payments at the beginning of each month, there you have a case where time triggers actions. So it was eventually realized that time has a mathematical structure independent of the causal structure of change. So you separate out the temporal elements from the causal elements in your planning systems. And we'll see a lot when I talk about the applications at the end. We'll see planning systems involve this sort of separation of temporal temporal structure with causal structure. So then we can start asking questions about time that are kind of independent from events and change, like is time discrete or continuous? Is it linear or branching or parallel or cyclical? How do you represent the flow of time? Is it bounded or infinite? Is the point of time fundamental or is the interval fundamental? What kind of granularity are you talking about? Are you talking in terms of what is the fundamental unit of time? So all these sorts of questions expose the structure of time and the organization of time. And these early representations, like the event calculus and the time map manager, are all ways, like the event calculus is sort of based on this method of temporal arguments that I talked about earlier. And then there's a lot of work that we're not going to talk about as well, dealing with how do you map expressions in different time granularities, calendar information. So these are all kind of early AI representations of time, but most important for this tutorial are representations based on constraint reasoning. And in the early 80s, there were emerged sort of constraint-based approaches to reasoning in general. So a constraint-based representation is a representation of constraints as relations on variables. There are two classes of constraint processing algorithms. One is called search-based, which is different variations on backtracking, and we'll talk about those here. And then inference-based, which are based on constraint propagation methods, which are also called consistency enforcing methods. And both support a graphical view of time, as we'll see. The pioneering works on constraint-based reasoning in general include the paper by Montanari in '74 called Networks of Constraints, the paper by Mackworth in '77 called Consistency in a Network of Relations, and Eugene Freuder in '78. These are kinds of the early first papers on constraint-based reasoning. The two really important papers, I think, to look at if you really want to find the foundation of the approaches that we're going to talk about today, they all kind of boil down to these two papers. James Allen in 1983, Maintaining Knowledge About Temporal Intervals, that was published in the Communications of the ACM, and Dr. Mary Pearl, Temporal Constraint Networks, published in AI Journal in 1991. I think myself, I'm not sure my co-authors agree with me, but I think that virtually everything we're going to be talking about in this course, this tutorial, basically stem from one of these two papers. This is really the foundation of the approaches that we're going to talk. And kind of interestingly, most of the approaches are based on either one or the other, but not both. There's a few attempts to sort of combine these two techniques together, but on the whole, there's kind of a partitioning of reasoning methods based on one or the other of these papers. So virtually everything we talk about for the rest of this tutorial starts from one or the other of these papers. Okay, so are there any questions at this point? Because I'm going to turn it over to Roman, or if there are any questions for me before I turn it over. It's just sort of a broad introduction to.
Okay, so good morning. My name is Roman Barták, and I will try to be your guide through the era of some core formal models for describing time, and I will also include some algorithms. So this will be more technical part of the tutorial, but I will try to be as clear as possible without going into really deep technical details like proofs and so on. But still, if there is something which is not clear, don't hesitate to interrupt me and ask questions during the talk. So first, let's start with a simple question. What is time? Or if we want to model time mathematically, we need some mathematical structure which describes time, flow of time. So this structure could be some set, and the set should satisfy properties of having a transitive and asymmetric ordering relation. Meaning, if A is before B and B is before C, then A is before C. That's a transitive ordering relation. And it should be asymmetric. If A is before B, it's not possible that B is before A in time, right? So that's the core mathematical structure. The set could be either continuous, it could be real numbers, or it could be discrete. It could be, for example, integer numbers. Basically, when we want to use time in AI system, or more specifically in a planning and scheduling system, it's like with everything in AI. So we have some knowledge base, in this case, a knowledge base containing temporal references and relations between them. And we can ask if this knowledge base or database is consistent, so we can verify consistency. Like if A is before B, B is before C, and C is before A, we know that this set of relations is not consistent, so there is some problem. So we can verify consistency. We can infer more information from the network. So if A is before B, B is before C, we can infer that A should be before C. Or we can ask queries, meaning we can ask if something can be true together with a given set of temporal relations. There are basically two approaches to model time. And Robert mentioned actually two papers that started these two approaches. So the first approach is qualitative one. In qualitative approach, it means that we are not working with numbers. So we capture time relations in a relative way. A is before B, or interval C meets interval D. So there are no numbers, just relative relation between the temporal assertions. Or if asked, we can use quantitative approach, meaning we will have numbers. We will have more precise information about distances between time events. So something we can say, A started 23 minutes after B, or at least 23 minutes and at most 40 minutes, or something like this. And I will now describe both of these approaches separately, and at the end I will show that actually we can combine them somehow together, even if not a lot of people are doing it. So let's start with the qualitative approach. So as I said, in qualitative approach to model time, we use relative relations between temporal references. And I will use an example to demonstrate all these techniques through this part of this tutorial. So I'll be adding more and more information to this example. So it's a very simple example. It's describing some process. I read newspapers during breakfast, and after breakfast, I walked to my office. So we can see there is some information about time, during, after, and so on. And now the question is what we can do with this. So we can represent it somehow. This is a form of Gantt chart that we can use to describe this relation. So we have some activity having a breakfast with some start and end. We have activity for reading newspapers with start and end. And it should be during having the breakfast. We have activity for walking to office with some start and end. And we started to walk to the office as soon as we finished breakfast. And now there are at least two ways how we can describe these activities more precisely. So the first way is using intervals. That's on the left side. So we can use temporal intervals corresponding to duration of activities. So we have three intervals here. So we have three nodes in this network representing these intervals: having a breakfast, reading newspapers, walking to office. But there are some relative relations between these temporals. No numbers, just relative relations. So we can say that reading newspapers happened during having the breakfast. And having the breakfast was right before walking to office. So we can describe relation between intervals. Or we can use time points. The interval has a start time and end time, like here. So we can represent each of these time points or time instance as a separate node in the network. And then we can describe relations between these time instances. So we have starting of breakfast, which must be strictly before ending the breakfast, right? Or reading newspapers started late after starting breakfast, but it could start exactly the same time, and so on. End of breakfast was exactly when we start walking, so there's equality relations there. So we have these two approaches to model time in a qualitative way, either using intervals or using time points. Even if the approach with intervals is actually older, I will start with the time point because it's easier to explain these concepts, and we will then transfer these concepts to intervals. So when we model time in a qualitative way, we will be using temporal references, which is a description of something that happened or something that was true for some time. So as I mentioned, we will be working with two types of temporal references: time points or instants that describe change in the world, or time interval, period, describing when something was true or something happened for some time. And between these temporal references, we describe temporal relations, which are relative relations between points or between intervals, or even together between points and intervals. So they describe some relations of ordering between these references, right? And as I mentioned, the typical problems that we need to solve is if we had such a set of temporal references and temporal relations, is the set consistent? So we will need some algorithms to verify consistency of this temporal database. We want to ask queries to this database. Like in our example, we may ask query, did I read newspapers when I entered the office? Well, it's obvious for you, but I will show you how to formally deduce the answer to this question. Or we can try to deduce some extra information from the temporal network. We will be talking about minimal networks, meaning we will deduce information that is inevitable, must be true, definitely, in the world that is described by a given temporal database. So as I said, I will start with the description of qualitative approach, quantitative approach using time points. So we were talking about some symbolic calculus to process time points and relation between the time points. So in this calculus, we need some primitive relations. For time points, it's quite easy because we have a linear time. So there are just three relations between the time points. Either one point is before the other one or after one, or they happen exactly at the same time. Of course, we don't always know these primitive relations, so we perhaps don't know that something happened strictly before something else, so we may combine them together. So to express a temporal relation between 2 points, we can use a set of these primitive relations. So for example, this set, small or greater, means these 2 time points happened at different times, not at the same time, right? The last set says, oh, we have no information about the temporal relation between these time points, right? What do you think is the first set, empty one? If I have an empty relation between 2 time points, what does it mean? I usually ask questions to my students to wake them up. So.
You know that you don't know anything about it?
No. That was, yeah, exactly. That was the last one. So if you have no information, that's the last one. Before equal after.
The last one could also be that you know that there is no ordering between them.
Yes, yes, exactly. So this empty relations means actually it's inconsistent, right? So there is no relation, no possible relations between time points, meaning this set of temporal references is not consistent. So when we deduce during inference empty set, it means inconsistency, right? Okay, so these are primitive relations. We will describe them using this formalism, time point, set of primitive relations, and another time point, right? And point algebra is a mechanism to work with these relations, and as I said, without numbers, without really using numerical time. But if we are talking about algebra, we need to define also relations between these. We need to define operations between these relations. So these are the primitive relations, and now we can combine them, right? So as we represent them as sets, we can use set operations, but basically these set operations describe logical operations like conjunction and disjunction. Right? So if I know that there is some relation between point T1 and T2, and I know there is another relation between point T1 and T2, I can make an intersection of these sets to obtain a more precise description of this relation. Or if I know there is some relation or another relation between 2 points, it's a disjunction, so it can be described using union of these sets. So these are quite simple operations. More interesting operation is a composition. So when I know that there is a relation between points 1 and 2, and there is a relation between points 2 and 3, using the composition operation, I can deduce relation between point 1 and 3. And this table describes how the primitive relations are combined together. So for example, if I know that point 1 is before point 2, and point 2 is after point 3, then I know nothing about the relation between point 1 and 2. P is the complete relation before, equal, or after, right? Or if I know that point 1 equals point 2 and point 2 is before point 3, then I know that point 1 is before point 3. Right? So this table describes how we can compose these primitive relations. Of course, if we have a set here, then we combine any element of this set with any element of this set using this table to obtain the result. Right? So this is composition relation. The most widely used operations are the intersection and decomposition. Why it's most widely used? Because we may have some information between points T1 and T2. There might be a third point. So we may have an information about the relation between point 1 and 3 and 2. So I can combine this information through the composition operation to deduce new induced relation between points 1 and 2, and I can intersect it with the original information that I have, right? So you will see this formula quite frequently. Those of you who are familiar with constraint satisfaction techniques, they already know this formula because it's called path consistency in constraint satisfaction. But you may also know it from other algorithms like the Floyd-Warshall that I will describe later. It's always the same story. Okay, so how we can do the inference? So this is our example. I read newspapers during breakfast, and after breakfast I walked to my office. So I can represent it using this PA network, point algebra network, with nodes corresponding to times and arcs describing the relations. And now I ask the question, did I read newspapers when entering the office? Well, so what does it mean? It means that I need to find some relation between reading newspapers and entering the office. So if I transfer this question, this query, into more formal description, I am asking if this is true. If I started reading before finishing working, which is the time when I entered the office, and I finished working, and then I still read. So I finished reading after that time, right? So if you look at it, this is obviously true. I can find this relation here, right? So I will not look at this relation. I will focus if this relation is consistent together with this network. Right? So I will add it to this network, and I will try to deduce if it's still OK. So what I do is I find a path between these two time points, the end of reading and the end of working. And now I combine all these relations together to deduce a new information between these two time points. So I combine the relation between end of reading and end of breakfast with the end of breakfast and start of working, and start of working and end of working. So this is the composition relation. I take everything from this table, and then this gives me the induced relation between these two time points, and I compare it with what I'm asking about. If WE, the end of working, is before the end of reading, right? So this is this relation. Okay, so if I do it, I need to do these operations, and this will be the result. So I can deduce that the point RE is before WE, but at the same time, it should be after, right? So the intersection is empty, so I know this is inconsistent. So the answer to this query is no. It's not possible. There is no way that I read newspapers when I entered the office, right? So this is a formal approach how to do it. Of course, I describe it in an ad hoc way for this particular query, but we can generalize it as I described before. We take the query, perhaps we can make a negation of this query, add it to the network, and ask if it's still consistent or something like this, right? Okay, so how we can verify the consistency? So first the question is, what does it mean that the network is consistent? So we can represent the temporal database as a network, as I described before. So we have points corresponding, we have nodes corresponding to points, and if there is some relation between the points, we have an edge or arc between these 2 points. So this is called a PA network. And we say that this network is consistent if we assign times to all time points in such a way that all the relations are satisfied, are consistent, right? So this is the way how we define the consistency through numbers. So we need to find precise times of all these events and have them consistent. But we will not be using numbers to deduce consistency, because there is a simple claim that claims the network to be consistent if from each set of primitive relations between any pair of time points, we can select exactly one before, equal, or after. And if we select Z1, and if we combine any two relations to induce a new information between points I and J, then this relation should be in the combination of these two, meaning it's somehow locally consistent with them. Right? And it's a nice claim, because now we can use it to deduce an efficient procedure to verify consistency. And this procedure is basically based on path consistency, meaning we will repeat this operation until something is changing in the network. So we take all triples of nodes and we combine them. So we take the information I, K, Kj. Using the composition, we deduce something and we make an intersection with the original relation between I and J. And if we deduce that there is some empty relation in the network, then the problem is not consistent. But the nice thing is that if we do not deduce empty relation, we can claim the network to be consistent. So path consistency is a complete verification technique for point algebra. Okay, and as I said, the empty set means inconsistency. So if we do not deduce empty set, we know the network is consistent, right? So what we know is that path consistency can verify whether the network is consistent. But it does not mean that it removes all inconsistencies from the network. Right? So let's look at this simple network. 4 nodes, SE, T1, and T2. And we have this relation, small or equal. Does not equal means smaller or greater. And small or equal relations here. If you apply path consistency to this network, the answer will be yes, it's consistent. And no primitive relation will be removed. So for example, if I take this path, S, T1, and E. So I have small or equal, small or equal. If I combine them together, I obtain small or equal. And that's the relation between S and E, right? So it's there. If I take this path, T1, T2, and E, it's smaller or greater, small or equal, meaning yes, that's still okay. Small or equal is satisfied on this path, right? But if you look at this network, you may say, oh, but there is a relation which can never be true. This is called a redundant relation. So there is a primitive relation between 2 time points that can never hold in any word. So look at it carefully if you can find which relation, primitive 1, can't be true. Can anybody see it?
S and E can never be equal.
Yes, exactly. It's the equality relation between S and E, right? Why? Well, we know that T1 and T2 are 2 points between S and E, and they are different. So even if there is possible equality here, or here, or here, or here, meaning S can be equal to T1, E can be equal to T1, or S can be equal to T2, or E can be equal to T2, it can't happen together. Meaning this equality can never be true in any word. And path consistency is not able to deduce this information. Meaning path consistency is not making the network minimal. So if you want to make the network minimal, it means that we remove all inconsistent primitive relations from it. So minimal network is something like every relation that remains in the network is true in some word, in some possible word, right? So path consistency is not enough. We need a stronger consistencies like 4 consistencies from constant satisfaction to construct minimal networks to remove all inconsistencies. Okay, so that was about point algebra. Any questions so far? So the nice thing about point algebra is that it's tractable, meaning we can solve these problems in polynomial time. Okay, there are no questions, so let's move to the interval algebra, which was actually an older concept by Allen, and point algebra was proposed later as a tractable subclass of interval algebra. So in interval algebra, we will be working with intervals, not with points. Even if interval is somehow represented using 2 points, start time and the end time of the interval, right? Now we have more relations between intervals, right? In between points we have just 3, but if you look at intervals, there are much more relations. So one interval can be before the other one, right? And if we move this interval, they will touch, meaning it meets like this. And if we move it even more, then they will overlap like this. And if we move it even more, then we can say that one interval starts that interval. If we move it even more, then it's inside. And if we move it, then it's at the end of that interval, right? And of course, specific relation is that two intervals are exactly equal, right? And if we continue, we obtain these 6 relations on the other side, right? So if I say something is before, I can say in a reverse way that y is after x. So in total, we have 13 relations. I will use these symmetrical relations with the word I, like inverse or something like this. So bi means actually after, right? So it's an inverse relation to before. And like before, we have 13 primitive relations, and we can combine them in a set. So now we have 2 to the power of 13 possible relations between 2 intervals, including relations that we are not exactly sure what the relation is. Like it could be before or after, or they are somehow overlapping in various ways, right? So, of course, that's quite a lot of relations. So sometimes if you want to solve a particular problem, we don't need to work with all these possible combinations of relations. So for example, if we want to model unary resource is a resource where 2 activities cannot be processed at the same time. So no overlap of activities is allowed. So to model unary resource, it's enough to have just the relations before or meet, and the reverse, after and meets at the end. And that's it, right? So we can work just with a subset of these intervals to model particular world. Like before, we can define intersection, conjunction of intervals, or union, disjunction of interval. We can define also the composition operation, but please don't ask me to show you the table because it's a 13 times 13 huge table, right? But we can define it for 2 parts of intervals. Like before, we can define the interval algebra network. I already showed you how the network looks. The nodes are intervals. The edges describe one of these relations between these intervals. Again, we can define consistency of this network, meaning we can assign start times and end times in such a way that all the relations are consistent. And still this claim is true, meaning we don't need numbers to deduce consistency. We can select from each set of relations between 2 intervals exactly one. And if we select it and this relation holds, meaning this relation is still in the composition of using third interval, then the network is consistent. Unfortunately, path consistency is no more a complete technique for verifying consistency of interval algebra. Meaning, if we apply path consistency algorithm, it's the same algorithm like before, just the operations are different. And if we deduce that some relation is empty, we know the problem is not consistent. That's fine. But if path consistency says it's consistent, it does not mean that it's consistent according to this definition. It's path consistent, but it does not mean that there exists a solution. And this is an example of an IA network which is path consistent, but it has no solution. We don't have a table here to draw it, but we will put the slides on web so you can check all these relations and you can verify that there are 4 intervals and it's not really possible to allocate these intervals into time in such a way that these primitive relations are satisfied. So now you need to trust me that this example is correct, but you can verify it later. So the problem is that for interval algebra, checking or verifying consistency is actually a hard problem. So it's NP hard. While for point algebra, it's tractable. We can solve it in polynomial time. As I said, or it may seem somehow strange, because you can say, I have interval. So interval consists of 2 time points, right? So I can take these time points, and I can convert interval algebra into point algebra, right? So where is the problem? The problem is that if you look at relations between intervals and you use time points, let me go back to this slide. So actually I did it here, right? So these are the relations between the time points. But the problem is that these relations are no more binary relations between two time points. If I combine them, I may obtain relations of hierarchy. But in point algebra, the relations were always between two time points, not between 3 or 4. And that's the difference. So yes, we can convert relations from interval algebra to relations in point algebra, but these relations will be somehow n-array relations, not just between two time points, right? For example, if you see here, this relation is between 4 time points already. Yes, yes. In this case, yeah, you are right. In this case, for primitive relations, it's okay because they are conjunctions. But if you combine them, like if you say before or meets, then you obtain a disjunction, exactly, right? So for primitive relations, it's okay, but if we combine them, we have disjunctions, and that's a problem. Okay. So that's about the interval algebra. Just one slide, even if the concept is very important, still the ideas are somehow similar for all these algebras. So what we can also do is we can combine these two things. So we can combine intervals and time points. And you may ask why we need to do it, right? Well, the reason is that if I have interval, I have start point and end point, but these points are somehow different than points in the point algebra. Let me show an example. A light bulb is off, and after switching to toggle, the light becomes off, right? And now let's ask the question, what's the situation with the light in the point when I switch the toggle? Is it on or off, right, at this point? We don't know. We can model it using two intervals, and there is no problem. I have two intervals. One interval, the light is on. The other interval, light is off, and they are meeting. No problem, right? But if I introduce really the point in between, and if I ask, so what's the status of light at this time point? I don't know. Is it on or off? I have no answer, right? So it's useful to model both intervals and both time points together because they have a slightly different meaning. Okay, time points are the edges of the interval, but the meaning is very specific. If we have a time, we need to know something about the time, right? So we don't know if the light is on or off. Right, so that's the way why we are introducing an algebra that combines both intervals and both time points. So we can describe relation between time points and intervals. So this is basically the extension of relation that we need to do to have this algebra. So we have all 13 relations from the interval algebra. We have 3 primitive relations from the point algebra. And we have these 5 extra relations describing relation between point and interval, which is quite straightforward. Before, at the beginning, inside, at the end, or after, right? The relation of point and interval. And then again, we can apply all of these techniques that I described before. And you may expect that, of course, verifying consistency is hard because we have the intervals here, so it's still be hard. Okay, so that was about qualitative approaches. Any questions so far? Okay, so let's move to numbers. But I will use the same example as before. I just put some numbers there, right? So I got up at 6 o'clock, which is not true because I got up at 5 o'clock today. But okay, I read newspapers for 30 minutes, which is also not true because I didn't read anything today. During breakfast, I had breakfast, great. After the breakfast, I walked to my office, meaning I walked to conference venue, which took me an hour, not true exactly. And I entered the office at 8 a.m., right? So now we have numbers. And we have more precise information about distances between time points or durations of intervals. And then we use these quantitative approaches to model this, right? So again, we will use time points, like, what is it? starting of breakfast, which is exactly when I got up, ending of breakfast, and so on. I assume that I need at least one time unit between starting and ending the breakfast to enjoy it, really, so at least 1 minute is there. I started reading sometime after I started breakfast. It took me exactly 30 minutes, so this interval is the minimum and maximum distance between the time points, and I finished reading before the end of breakfast. This time is some beginning of time. In this case, I use midnight to describe relations like I got up at 6 o'clock, which actually means I got up 6 hours after midnight. So I have this time point describing the midnight, and that's the minimum time in minutes, 360 minutes. I don't know what's the upper bound, but I know that I entered office at 8 a.m., which is 480 minutes from midnight. I hope it's correct. Okay, so that's the problem. And of course, now I can ask, is this information consistent? Is it really possible to do it this way? Or I can ask other questions, like, when did I start my breakfast? Okay, I know that I started at least at 6 o'clock, right? That's from the midnight. But I don't know when I finished. So I can now deduce what's the end time of my breakfast. It's not written here. If you look at the description, I did not say I finished my breakfast at some time, right? So let's deduce it. So that's what I know. I got up at 6 o'clock, and because I have a breakfast after it, so I have the lower bound for the start of breakfast. About the upper bound. Okay, so now I know that the breakfast started before reading newspapers, and reading newspapers finished before ending breakfast, and so on. The duration of reading newspapers was 30 minutes. And after the breakfast, I immediately started to walk to the office. It took me 1 hour, and I was in the office at 8 a.m., right? So now I can use this information. I can put it together, and I can deduce when I finished my breakfast, right? When was the last possible time when I can start my breakfast to be consistent? So BS is more than RS. That's here. RS equals RE minus 30 from this relation. What I can do, RE is before BE, so that's this relation. BE is the same as WS, as this step. What's next? WS is WE minus 60 from this relation. And now I can substitute. I know WE is 480. So 480 minus 60 minus 30 is 390. So the answer is, yeah, I started my breakfast sometime between 6 o'clock and 6:30. Right? So I deduced new information which was not explicitly included in the initial description by reasoning with times. Okay, so how we can do it in general? So in these quantitative frameworks, we are working with time points. They describe exact time, and the relations are numerical, meaning these relations describe distances between time points. It could be absolute relation or unary one, which says this time point happened between 6 and 8 in the morning, right? So we specify absolute relation, which is not really absolute because it's relative to midnight, as I will show you in a minute. Or we can describe temporal distance between time points. The minimum distance, Aij, or the maximum distance. So something happened at least 10 minutes and at most 20 minutes after I finished breakfast, right? And as I said, actually the unary relation can be converted to binary relation if we introduce a specific time point, the beginning of the word, or something like this, reference time point T0, which could be 0 in this case, right? And then every relation can be described as a binary relation. So we will be working just with binary constraints, and the constraints will be defined by a minimum and maximum distances between two time points, right? Okay. We can use these junctions of temporal constraints, but I will be talking about it later. So far, we will be using just primitive constraints. So if we do not use these junctions, we obtain what's called a simple temporal network. And that's basically the major result from the paper that Robert mentioned at the beginning, the other one. So in simple temporal network, we allow just what's called a simple temporal constraints. Between any two time points, we define minimum and maximum distances. That's it, no disjunction, right? And the possible operations, like we did for the point and interval algebra, are some composition relations, meaning if I know the distances between points I and j and k, I can deduce the distances between points I and k. And it's very simple, right? I make a sum of minimum distances, and I make a sum of maximum distances, and this defines the minimum distance between the beginning and end of this path, and the maximum distance between them, right? And similarly, I can define intersection. If I have two different informations about distances between two time points, I can make an intersection to deduce what's the real distance between them. So I take the maximum of the minimum distances, because both of them must be true, and I take the minimum from the maximum distances because most of them must be satisfied, right? So it's easy. It's just a combination of inequalities that I described before, and this is what you get, right? We say that simple temporal network is consistent, again, if we can assign particular times to time points in such a way that all these relations are satisfied. And I think is, again, path consistency, exactly the same algorithm as before, I will show it in a minute, is a complete algorithm for simple temporal network. So if we have a simple temporal network, we run path consistency algorithm, and it says, yes, it's consistent, then we know that STN is consistent, meaning there exists a solution to this problem. Another option to path consistency is using a famous Floyd-Warshall algorithm. This algorithm is called all pairs shortest path algorithm, meaning it's an algorithm that for any 2 points computes minimum distance, right, between these time points. But if you look at it, you say, oh, but we don't have a one number in H. There are 2 numbers, right? Minimum distance and maximum distance. So first, before we can apply Floyd-Warshall algorithm, we need to convert the simple temporal network into a classical graph with nodes and arcs annotated by distances. And then we can apply it for Floyd-Warshall algorithm. So how we can do it? We define what's called a distance graph for a simple temporal problem. So if we have this relation minimum and maximum distance, in the distance graph, we will be using just the maximum distances between time points. So we will take the relation Bij as it is, but we will convert the minimum distance to a maximum distance between these 2 points in a reverse order, right? It's the same, just a mathematical operation, this multiplied by -1, right? So this is what you get, so minus AI. So now we obtain a distance graph, and if we find a negative cycle in this graph, it means inconsistency. Because it means that something should happen before it actually happened, right? So that's like A before B, before C, before A. So that's the same here. So negative cycle means inconsistency. So this is the original simple temporal network, and that's the distance graph for it. So you can see it has the same type of arcs, but just they are oriented in both ways. So the minimum distance is going in the opposite direction with the minus symbol, and the maximum distance is here, right? And now we can use Floyd-Warshall algorithm to compute all pairs shortest path algorithms. So if you look at these algorithms, path consistency is basically an algorithm that finds a transitive closure of all these relations. So again, it's exactly the same principle as for point algebra or interval algebra. So we take all triples of pairs I, J, and K, and we combine IK, KJ to deduce a new relation between IJ, and then we intersect it with IJ, right? The nice thing for simple temporal network is that we don't need to run a PC in general, because in general, path consistency is repeated until something is changed, some domain is changed, right? For simple temporal network, it's enough to run path consistency just in one iteration. So we don't need this repeat until loop, we just need for each loop. So the time complexity is n to the power of 3, where n is the number of nodes. But the rest is the same, the same operation. And if we deduce that some relation is empty, we know that the problem is not consistent. Right? The nice thing about path consistency is that this is an incremental algorithm. Meaning, if we make the problem path consistent, and if we add a new relation to this algorithm, we don't need to run it from scratch. We can run this algorithm from this new information, and that's spread to the rest of the network. So it's faster than running it. Of course, in the general case, you may obtain the same time complexity, but in practice, it will be faster than running the algorithm from scratch. So that's path consistency. For the Floyd-Warshall, as I said, it's an algorithm to find all pairs shortest path, so minimum distance between any pair of nodes. So we need to deduce, we need first to convert the temporal network into distance graph, and then we use the Floyd-Warshall. If you compare these two algorithms, you can see very similar principle, right? So we have a composition and intersection, and in Floyd-Warshall, we have a sum and minimum relation, right? So both algorithms are using similar principles, and you can find these principles in many areas of computer science. For example, in Kleen's theorem, in automata theory, uses exactly the same principle, making a transitive closure of something, right? So as I said, the simple temporal network will be consistent if there is no negative cycle in the graph. So if we deduce that the distance between I and I is negative, the minimum distance, the network is not consistent. Okay, so that was about the simple temporal network. Sometimes it's not enough to model problems using simple temporal constraints. And we need a more extensive framework. So what we can do is we can use these junctions. So again, the same example, slightly extended. So yes, we know this. And there's new information. I entered office exactly the same time when Peter left home at 7 a.m. And now there is this new information. I know that Peter is going to office either by car, which takes him 15 to 20 minutes, or by bus, which takes him 40 to 50 minutes. Right? So it's a disjunction. I don't know which means of transport Peter was using today. I just know that we met in the office, but I can deduce what he used. Right? So we need to express disjunctions of simple temporal constraints. Simple temporal network is not enough to describe this problem because we have these disjunctions, right? It's described here. So the difference between the end of Peter's walking or travel to office minus the start of Peter's travel to office is either between 40 and 50 or between 15 or 20, right? So this is what's called a temporal constraint network. So it's basically simple temporal problem where we allow specify distance between two time points not as a single interval, minimum and maximum distance, but as a set of intervals. That's the difference, right? So we can specify disjunctions of simple temporal constraints, but over the same, should be variables, over the same pair of temporal points. So it's not general disjunction. You will see later that for general disjunction, we have a slightly different framework. So between the same pair of relations. Again, everything else the same. We define the composition relations, intersection. Of course, now we are working with sets of intervals, so not with intervals. So when we combine these relations for intervals, we obtain interval again. Now we have set of intervals combined with set of intervals. So we obtain a set of intervals that could be much larger than the original sets of intervals, right? Definition of consistency is exactly as before. So we say that the network is consistent if we can assign values to time points, satisfying all the temporal constraints. Unfortunately, if we introduce these simple disjunctions, path consistency is no more enough to verify consistency of this network. Again, if path consistency says it's not consistent, then it's not consistent. But if path consistency says, yes, it's path consistent, it still does not mean that the network is consistent. So it's not enough to apply path consistency. There is a quite straightforward but exponential approach to deduce consistency of a temporal constraint network or temporal CSPs. This is based on some form of meta-reasoning. And the idea is very simple. Those of you who know constructive negation in constructive disjunction in CSPs, this is exactly the same idea. So I have disjunction, I have another disjunction. So what I do is I combine these two disjunctions, meaning I combine parts of this disjunct, and I obtain different problems, and I solve them separately, right? So I decompose the temporal network with disjunctions into a set of simple temporal networks when I introduce all combinations of all these disjuncts. And for STN, I can use the polynomial algorithm, and then I combine the results of these polynomial algorithms for making the problem consistent to verify consistency of the original temporal CSP, right? So, of course, when we decomposing the temporal network into this set of simple temporal networks, that's where the exponential blow may appear, right? Because if I have disjunct with 3 elements, another one with 3, I obtain 9 simple temporal networks because I need to combine all of these together, right? So 3 times 3. So that's when I may obtain the exponential increase of the size of the problem, right? So as I said, if I have the STNs, I can solve them separately using path consistency, and then I can combine the results. So let me show you how it works in this example that I presented before. So this is temporal constraint network, and I use just one disjunction here, so it's very easy. I don't need to combine more disjunctions. But still, it's there. 1520 is the distance, or 4050, right? So from this network, I just obtain 2 components STNs, right? One is for the distance 1520, and the other one is 4050. Now, this is STN, so I can run path consistency to make the network minimal, right? And I can realize that actually this network is not consistent. There is no way that it happens, that these points are in these distances. So if I then combine these 2 networks, I just use this last network as the solution. So actually, now if I ask what means of transport Peter was using, well, it was bus, because there is no way that information that I know was consistent with going by car, right? So that's interesting, right? We can deduce something which is definitely not temporal relation, going by bus, by temporal reasoning. Okay, so that was simple disjunction between pair of variables. But we may need even more disjunctions, right? So now forget about me, and let's focus on Peter. So yeah, we have some information about Peter, and we know that, okay, where is it? Yeah, he was jogging for 40 minutes before leaving home, and he had breakfast for 20 minutes before leaving home. And then he went to the office either by car or by bus, which took him 15, 20, or 40, 50 minutes. So now I have 2 activities, breakfast and jogging. I can describe it using this temporal CSP. This is the disjunction. But it does not say the whole story, right? Something is missing. Can you see what's missing in this network?
The order between breakfast and jogging.
Exactly, yeah. I suppose that people are not having breakfast together with jogging, even if some people can do it. So these 2 activities should not overlap, right? But I don't know the order. It's not specified in the problem description, right? So I only know that breakfast and jogging should not overlap. So either I finish breakfast before jogging, which is okay, or usually we do it in the other way, jogging before breakfast. So we need to express disjunction again, but if you look at this disjunction, it's not the same disjunction as before, because now we have 4 variables in that disjunction. In disjunctive, in temporal CSP, there were more disjunctions between the same pair of variables, right? So it's a more general disjunction, and this is called a disjunctive temporal problem. Right? How to solve this problem? Exactly as temporal CSP. So we describe the component STNs, and we solve them separately and then combine the information together. Right? So the principle is the same, even if the concept is even more general, because there could be a more general disjunctions. Okay. So as I said, the same way, decomposing two components CSTN. Let's make it even more general. So in this example, there were 2 activities, breakfast and jogging. But both of them happened. We know that we did both, or Peter did both breakfast, had breakfast and did jogging, right? But sometimes we need to model relations that are disjunctive, but in terms of one of them happened, not both, right? So for example, we can say, when Peter goes by car, then Robert joins him, and they go together. Otherwise, Robert goes by train, which takes him 45 minutes. Right? So if you want to describe this problem, we have several activities. Right? Going by car. Going by car is shared both by Peter and Robert. Or going by train for Robert, or going by bus for Peter. So yes, we can describe all these activities, start times, end times, in a single network. But now the major difference is that not all the time points are included in the solution. We need to select, right? Either we will go this way for both of them, right? Or we will go that way for both of them. So these 2 time points may be in some solution, or may not be in the other solution. Right? So this is what we call temporal network with alternatives, or there is another very similar concept called TPN, temporal planning networks. In temporal planning networks, all these alternatives must be somehow nested. In the TNA, they does not need to be nested. The major difference is that in addition to simple temporal relations like here, we also specify what we call branching or logical constraints. And their meaning is that if there is a parallel branching, it means that if this node is selected, then both these nodes must be selected. Or we may have alternative branching, which says if this node is selected, exactly one of these nodes are selected, right? So we go either that way or this way. So that's the alternative there. Parallel branching is the classical branching in temporal networks. Everything happens together. So the alternative branching is the main difference. So you may select different passes through this network. So this makes the problem even more complicated because now we are not doing just the temporal reasoning, but we also need to select a subset of nodes corresponding to all these branching relations. So for example, these 2 nodes, these 2 nodes, and these 2 nodes are okay. They satisfy the branching constraints. Or these 4 nodes or these 4 nodes. That's the other solution regarding the selection of subset of constraints. Right? So this is called TNA, temporal networks with alternatives. We have the parallel and alternative branchings. And again, verifying consistency is NP complete. Even if these constraints are simple temporal constraints, it's still a hard problem. So it's easy to show that it's still NP complete. If there are precedence relations and if there are some other restrictions, we can do a consistency in polynomial time. But in general, with simple temporal constraints, it's NP complete. Okay, yeah, as I said, to solve this problem, we need to select the nodes to satisfy both the branching constraints and the temporal constraints. Okay, so let's make it even more general. And this is the most general framework I will present here. And it has a very long description that I took from the original paper from Mary. So it's a very different example, which is about, again, traveling to work. We like it to use this example to model temporal networks. So we have two guys, John and Fred. They work for a company. Local main office does not matter. They usually work at the local office, which takes John less than 20 minutes and Fred 15 to 20 minutes to get to work. Okay, twice a week, John works at the main office, which takes him at least 60 minutes. And we know that today, John left home between 7 and 7:05, and Fred arrived to work between 7:50 and 7:55. And we know that they met at a traffic light somewhere, right? So it's a very complex temporal problem with some numerical relations, but also some qualitative relations, like, okay, they met at a traffic light. What does it mean? Well, it means that the intervals for traveling must be overlapping, right? So what we can do if we want to solve this problem, we can put everything together. So we can have temporal constraints, numerical one, between the points, start of John's work, John's way to the office, the end of his way, of his journey. There are temporal relations. It's between 0 and 20 minutes or more than 60 minutes. We have interval. That's the activity going to work for John. And of course, we have a relation between this time point and this interval. So meaning that this time point is exactly the start of this interval, and this time point is exactly the end, the finish of this interval. So we have time points, we have intervals, we have numerical relations, we have relations between time points and intervals in a symbolic way, and we have relations between intervals, again, in a symbolic way. This relation is described as they met at a traffic light, right? So we don't know the time point when they met. We know that two intervals must be overlapping, right? And that's called general temporal constraint network, and everything is there. Points, intervals, numbers, and qualitative algebra, meaning time algebra, point algebra, and relations between time and points. I have not seen anybody using this in practice, so if you're asking me. But it's the most general framework if you really need it. Okay, so let's conclude this part of this talk. So we talk a bit about each of these frameworks, and there are other frameworks. So I just selected the core of them, right? So there are other frameworks. So this is some summary of them. So you can see some of them are qualitative, some of them are quantitative, some of them are working with time points, some of them are working with intervals, and so on. Of course, the obvious question is, yeah, this is the most general one because it covers everything. So why we are defining a simple problem? Oh, question, yes.
Yeah, just a quick question. So for the general, it's a good question. So for the most general one.
Okay.
I'm having trouble seeing how it's the most general. Are there different branches, like we had in the temporal network with alternatives?
No, there are no, yeah. That's the only thing which is missing there. So this is somehow going in a very different branch of research, but in this case, there are no alternative selection of points or intervals that are included. Okay. So it's in the same style as temporal networks before, but not this.
Okay, thank you. Thank you.
So yeah, it's not the most general. We can still extend it, right, if we want. But it's still the question. Okay, so if we have these very general frameworks, why we should use the simpler ones? Any idea?
Because they're simple.
Yes. Maybe enough to use them, right? And some of them are even tractable. So that's a great difference, right? So if it's enough to use point algebra, we should use it because we can verify consistency in polynomial time. Why we should use anything more complicated, right? So of course, when we want to apply these frameworks to solve problem, we should select the simplest one, which covers what we need, because it's usually the most efficient one for handling verification, consistency, and so on. Right? But there are, as I said, there are other frameworks like this. For example, for interval algebra, in general, interval algebra is NP complete. But if we select subsets of interval algebra and still working with intervals, we may obtain tractable subclass of interval algebra. Right? So there are specific subclasses where we can deduce consistency in polynomial time, even if it's interval algebra. Okay, any questions? Surprisingly, I'm on time, which is not typical for me. So we have plenty of time for questions, if there are any.
Maybe a quick one. So I just remember that there is a temporal formalism called conditional temporal problems. Could you relate this to the alternative?
It's similar to the alternative. It will be presented in the second part of the tutorial. The idea is that we can specify conditions for the branches. In TNA, we don't have conditions, so we don't say if something happens, you should go this way, or if something different happens, you should go that way. It's up to the solver to select the alternative. So that's a difference between conditional networks and TNA. But Brent will cover these networks, and Brent will cover uncertainty and precedences. So these very interesting things for real-life problems. This is just core. These are just core concepts. Okay, there are no more questions. Yes? No. There are no more questions, and enjoy the coffee break. It's longer than usually. Hurry up because it will be overcrowded, and we will start at 10:20. So that 10:20 will be the second part about preferences. So, thank you.